we have already established all the axioms we started from last week for the integral of non-negative extended Borel functions. And now we go and give the missing proof of some of the properties that were postponed last week. First one, integral on a subset. Yeah, we said that integrating a function times an indicator is the same as integrating that function, but instead of integrating it against the measure mu, integrate it against the measure mu restricted to that set B. And well, how can we prove this? We have already proved this in case f was the indicator function of a certain set A. And now we can do the following. Since the integral is, we have proved this when f is the indicator, and since the integral is linear, we can instead consider, take aj, sum over j, and even multiply by some numbers aj, as long as these are finite numbers. Okay, we can, because it is the integral is linear, so all this sum here, it will go out of the integral and here as well. So since it holds for functions which are indicator functions, it also holds for linear combinations of them, and this means it holds for simple functions. And now once it holds for simple functions, if f is no longer a simple function, but instead is just a non-negative function, a non-negative extended Borel function, then what we can do is we take a sequence of simple functions that increase to f, and then we apply this identity, which identity is this one, that the integral on omega of fn indicator b, the mu, equals the integral on omega of fn with respect to the measure mu restricted to b. So this will be true for each of these fn's that are simple functions that approximate our function f. So we can take the limit, and by monotone convergence theorem, this will increase to the integral of f, indicator b, etc. And this will increase to the integral of f with respect to the measure mu restricted to b. So by taking limits, we get this also for the case of non-negative functions. So you see the pattern here. We started with a binary function. The binary takes only value 0 or 1, so it's always the indicator of some event. From binary, we went to simple just by using linearity of the integral. And from simple, we went to non-negative using the monotone convergence theorem. Here we use monotone convergence theorem, and here we use linearity. And now the last missing step that is still missing is how do we go from non-negative to a general functions? Well, then we do the usual trick. We separate f from being a negative part, a positive part, minus a negative part. When we do that, well, we see here what happens when we multiply f by a function that takes value 0 and 1. Well, we can just multiply each of these two by the same function. And this is what is being done here. We're replacing f by f plus minus f minus, and just using the fact that it will distribute for the indicator. Now here, in this, we use the previous case. What's the previous case? We have already proved that this property holds for non-negative functions. So we get, instead of the indicator here, we get the measure. And now we get them back together again using linearity of the integral, and then we get this as stated. This completes the proof. Now there is this property that we stated, referred to it as change of variable. And this happens when we have a map, f, that goes from one sample space to another sample space. And we have an observable, which means a real function defined on the target sample space. Then if we have a measure mu here on the source space, we can do two things. We can either make the push forward of this function mu and get some f star mu on this set. And then on this set, we can compute the integral of this function g, because this is a Borel function, a non-extended Borel function that takes values on the extended real line. We can either integrate that function using the push forward measure, or what we can do is to the pullback of this function g, which means take a function which goes directly from omega 1 to the extended real numbers, just given by composing f and g, and the resulting function of this composition, f composed with g, we call that the pullback of g. So instead of integrating g against the push forward of a measure, we can integrate the original measure against the pullback of this function. This was the statement, and now we give the proof, and the proof will follow exactly the same pattern. We have already given a proof in case the function g is binary. So g only takes two values, 0 or 1. We have proved this. Now using linearity, we can go from binary to simple. And using the monotone convergence theorem, we can go from simple to non-negative. This one using monotone convergence theorem, and this one using linearity. What do I mean by linearity? Well, replace G by a linear combination of G1 and G2, assuming that G1 and G2 both satisfy this equality here. Then, well, since the integral is linear, it will split for G1 and G2. The constants will go out of the integral. The same will happen here. So this property will hold. By linearity, we can bootstrap a property that we know to hold for binary functions. We can bootstrap it to simple functions. And again, using monotone convergence theorem, we can take Gn, non-negative Gn that increase to G, and do all the same property as usual. Limit and the integral will commute because we are in the monotone case. And this is how we get it for non-negative functions. And now we want to go from non-negative to the general case. And usually, how is it? How do we go from non-negative to the general case? We write, as usual, f to be the positive part minus the negative part. And when we do that, well, not f, g. Well, when we do that, well, just note that here we're integrating a function with respect to a measure. We can just separate. This is the definition of integral. And this here we can use the fact that we know already this to be true for the case of non-negative functions. And we can group them together. This will be the definition of this function here. And moreover, we can say that not only these two are the same, if one of them is defined, then the other is defined, and vice versa. And we can say that simply because if this is defined, this means either this integral is finite, or this integral is finite, or both. But this integral equals this integral, so we get the same property here and here. So either one of these will be finite or both, which means this is defined. And conversely, if this one is defined, we can make the same argument backwards and conclude that this one is defined. There was a little typo before when f star g, the pullback of a function g, is composing g with f from the right. So we are at f here to the right of g, not from the left as written in the previous scene. This would not make sense. And about the previous proof, this discussion that we made that this integral is defined if and only if this integral is defined. So we need to exclude the case of infinity minus infinity. And the same argument we just made here, if we go back to the previous proof that we made, that of integral on a subset, that integrating f on a subset, this, which by definition is the same as this notation here, integrating on b f mu. What we just proved, that this integrating on a subset is the same as integrating with respect to this measure. We have the same phenomenon here to observe. If one of them is defined, it means at least one of these two integrals is finite. But since these are equal, it also means at least one of these two is finite, which means this one is defined. And we can go backwards and say the same argument. If this one is defined, it will imply that this one is defined as well.